Okay, so today we're going to talk about probability and the idea of probability, but also sort of the functional way that we're going to use this concept of probability to understand how likely events are and how to build probability distributions of these kinds of events. And really, these probabilities and these distributions in and of themselves are probably not particularly exciting or interesting, but they are helpful and they are useful, and we will use them as part of our statistical analyses. So we need to know a little something about them and how they work and understand this concept of probability. And this first piece, we're probably going to spend a lot of time talking about this concept of probability and what it means. Okay, so we're going to get a little philosophical at first, and then we'll dive into some of the nitty-gritty here in a moment. So I like it when quotes sometimes can help explain particularly complex or complicated ideas. Okay, and so what I want you to get down is some of these kinds of quotes here and think about what they mean, right? Like this first one: primes are randomly distributed. Unfortunately, we don't know what random means. Okay, words like dimension or field or infinity are just conveniences for mathematicians and scientists. They don't really describe reality, yet we accept them because well, somebody knows what that means. Like, what does dimension mean? Well, it's hard to explain, but somebody knows what that means. And then here's another example: when we have no explanation, we give it a name, and then now immediately that explains everything. And that's going to lead us into talking about probability here in a second. But before I go into some more quotes, I have a question for you to think about, and I want you to bring an answer to class with you. You get up in the morning and you look at the news, and it says that there's a 30% chance of rain. It's the weather forecast, 30% chance of rain. So my question to you is, what does that mean? Right? What does that mean to you? Right? And I want you to think about that, and I want you to bring an answer with you to class, and we're going to discuss it together when we get done with the quiz in class. I want you to think about an answer to this question. What does that mean? You get up, 30% chance of rain. What does that phrase, 30% chance of rain, mean? And we're going to talk about that, and it's going to get us into what I think is one of the most important concepts of probability, which we'll talk about in class. So, what is probability, right? And I want you to think of, what's your definition? If I asked you in class, what does the word probability mean? Like, what is your definition of probability? Think about how you would answer that. What would you say in response to that? Another thing that would be good to bring in class and to talk about, right? What is the definition of probability? You could look it up in your textbook, and your textbook has a definition of the word probability. It's on page 33. The chance that a particular event will occur in an uncertain world. Okay, cool. What the hell does that mean, right? What does it mean to say that there's a chance of a particular event occurring when the world is not deterministic or uncertain? So what does that mean? Well, it's problematic, right? Because we're asking about the word probability, and we're using the word chance to describe it. Well, you might say, well, what does the word chance mean? Fair question. Let's go to some dictionaries. What does the word random mean? HarperCollins Dictionary of Statistics. Random, occurring by chance, having no discernible pattern. Cambridge Dictionary of Statistics. Random, pertaining to a process or variable or outcome whose value changes on chance, or a process that simulates chance, often with implications, blah, blah, blah. Dictionary of Statistics Methodology. Random, having no specific pattern, purpose, or objective. See chance. You're like, oh, cool. All right, so they're all basically are using the word chance to describe probability. Cool. So let's go back and look up chance. HarperCollins, chance, a measure of how likely it is that some event will occur. Cambridge, chance, an unknown and unpredictable phenomenon that causes an event to result one way or another. Dictionary of Statistics and Methodology, chance, a measure of how likely it is that some event will occur. Huh. Seems like all of our explanations of what chance is have to do with this term likely and likelihood. What do those terms mean? Okay, what does likely mean? Let's look up what that means. Okay. Probability. A number between 0 and 1 represents how likely some event is to occur. Likelihood. The probability of a specified outcome. Does anyone see a problem with that? The word probability uses the word likely in its definition. The word likelihood uses the word probability in its definition. Okay? This is a problem. All right, we go down to Cambridge. Probability. A measure that denotes the likelihood that an event will occur simply by chance. There's probability and there's chance and likelihood again, right? Likelihood, the degree of certainty of an event occurring. Likelihood can be stated as probability. I don't know about you, but we're not really getting anywhere, right? And then Dictionary of Statistical Methodology, again, probability, assuming they're all equally likely. Likelihood, see probability. So So what's the point? The point here is that probability is one of those things that we use and we all think about, and I think we all, to a certain extent, sort of understand what that term means. But defining it is really hard, and we don't really know exactly what it means. We just sort of understand the concept, right? But you can't really define it without using terms like likelihood and chance, right? And then you can't define those terms without talking about probability. So it's very circular. Here are some more quotes here. Probability, a measure of ignorance. Being dimensionless, it is best used with a dimensional measure, especially a grain of salt. So what he's saying is we don't really know what the word probability means, and we should take that into consideration when we're talking about it. All possible definitions of probability fall short of actual practice. The fact that those best in a position to define probability cannot agree on a definition does not prevent biologists from effectively using probability, significance levels, confidence intervals, and other things within statistics. In fact, insisting on such an agreement would mean that modern statistics could not, even exist. So, basically, what we're saying here is that it's difficult to define the term probability, but that doesn't mean we can't use it, right? And that's the point of all of these series of quotes that we've gone over, right? We can use the idea of probability, likelihood, chance to understand how common an event is. And we're going to use that throughout the second half of the semester when we talk about t-tests and ANOVAs and correlation and regression and these kinds of things. These are all based on probabilities and the likelihood of an event occurring. Okay, so now let's start getting into the nitty-gritty. So we've spent some time talking about histograms and distributions of variables. So now we want to talk about probability distributions. Okay, so again, probability, the chance or risk that a particular event will occur in an uncertain world. If you have an event that is absolutely certain to occur, it still has a probability. That probability is just 1. Will the sun rise tomorrow? Probability 1. Yes, the sun will rise tomorrow, right? Was there going to be an eclipse on August 21st? Probability? Yes, 1. There was going to be an eclipse on August 21st. So events that are absolutely certain to occur have a probability of 1. Are we going to make it to the next second after this sentence? Just happened, right? So even events that are certain have a probability. Even events that will never happen have a probability. That probability is just 0, right? What's the probability that monkeys are going to fly out of my butt? Probability is 0, right? It has a probability, it's just very low. This reminds me of that scene from the movie Dumb and Dumber where Jim Carrey's talking to the girl that he likes, and he asks her, what his chances are with her, and she goes, "It's 1 in a million, Lloyd." And he gets this big grin on his face, and he goes, "So you're saying there's a chance, right?" So probabilities range from 0 to 1, right? 0 being absolutely no chance at all, and 1 being, will certainly happen, absolutely, with no chance of not happening, okay? So what we can do then is create a histogram, or a distribution in which the height of the bars indicates the probability of a certain event occurring, right? And we can capture all of the different probabilities of different events with a histogram, okay? So here we are, again, thinking about this foot length data that we looked at previously, and there we have bars representing the different foot lengths in our data set, right? Now imagine if you had, perfect information and lots of data, you could build these distributions that we see here on the right, where the bars represent the probabilities of these different, or the counts of these different data sets, these different ranges, right, these bins. So there's, about 11 counts in this bin right here, right? Now, if we were to change that from bins with counts into probabilities, we could make a smooth curve that's shown here, right? And that's our probability distribution. And it's a smooth curve because it covers every possible range of values. We don't have them into bins anymore, right? This is the possible range of probabilities associated with this particular variable, whatever it is. It's meaningless in this case. And so we can build a probability distribution of these data and use that, again, for useful things in biology, for statistical analysis, for understanding our data set. We can use it for something that is actually of interest to us. So again, a distribution of probabilities is this smooth curve that you see here, right? Where at any point along the curve, there's a probability of that specific value occurring, even down to 10.0132584996. Like there's a probability of that exact value, okay? And that is expressed by this curve along here. So if this seems confusing, we're going to go into some examples here. So let's start off with a real simple one. You flip a coin, right? Assuming it's a fair coin, assuming there's no problems with it. When you flip a coin, there are 2 possible outcomes. What are those possible outcomes, right? Pretty obvious. Heads or tails. That's it. So we can calculate probabilities, right? I'm going to flip a coin. It can either come up heads or it can come up tails. So heads is one outcome out of two possible outcomes. There's not a third outcome, right? Again, we're assuming that we're not flipping a coin on carpet and the coin's going to land, perfectly on its side or something without a head or a tail. Like if you flip it onto a flat surface and it's a perfect coin and it's a perfect surface, you'll get one of two outcomes, head or tail. Okay, and we can calculate the probability of that. The outcome of getting heads is one of two possible outcomes. So 1 of 2 is 1/2, 0.5. I'm sure we're all on board with that, right? Pretty easy to understand. Consequently, because there are only two possible outcomes, if the probability of getting heads is 0.5, then the probability of getting tails, by definition, also has to be 0.5, because they're mutually exclusive events, right? You can either be heads or tails, but you can't be both. It's impossible, okay? We'll talk about situations where it's possible to be both, but we're not going to spend a ton of time on those. So, head or tail, and each has the probability of 1/2. So now, we can graph these probabilities, right? It'd be a very simple graph, but we can do it. Probability of getting a head is 0.5, the probability of getting a tail is 0.5, okay? And we can show that with these bars. Now, imagine, right, that we were to push the bars together, and then we were to start throwing darts at the board, okay? Where the dart lands could almost be considered like your probability of, your chance, like each time you flip a coin would be like each time you throw a dart. And if it landed there, right, then that would be a head, right? So now you're saying, what is the probability that the dart will land in that H region? That's what we just calculated on the previous slide. It's 1/2, okay? So this area that we cover with this bar then represents the probability of that event happening. And we can calculate probability by finding the area of a shaded region of a distribution. Now this is a simple version with two outcomes and they're both equally 1/2. But if we go back a little bit here to this graph with this blue smooth curve here, that's also a probability distribution. And shaded areas of that distribution represent probabilities of getting those outcomes. Okay? And so we can use the same idea that we're using here also understand the probability of getting a certain value within a large probability distribution. Okay, and that's what is actually useful to us in biology. So let's start getting a little bit more complicated. We're going to build up to this over time. We're not going to jump right in. Sometimes there's more than two outcomes possible, right? Maybe you're going to flip two coins. Okay, each time you flip that coin, there's a 1/2 a chance of a head, a 1/2 a chance of a tail. But now if you keep going sequentially, now we're flipping two coins. Now, how many heads can you get when you flip two coins? Think about that for a second. How many different numbers of heads can you get if you flip two coins? 3 outcomes, right? You could have both coins come up heads, you can have one coin come up head and one coin comes up tails, or both coins come up tails, okay? And we can start thinking about what is the probability of these events happening, right? What is the probability of seeing each outcome? Well, the probability of getting two heads, we know what that is. It's 1/2 the first time and 1/2 the second time. Okay? Now, because there are 4 possibilities here, right? Heads, 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 tails, tails, heads, tails, tails, we know that getting heads and heads together is 1/4. The chance of that happening is 1 out of 4 possible outcomes. Now, you could say, oh, well, the probability of getting one head and one tail is, equally probable, so you might mistakenly say 1/3, 1/3, 1/3, but that's not true, because there's 2 types of one heads and one tails. That's where heads comes first, tails come second, or tails comes first and head comes second. And so we have 2 possible outcomes that have the same number of heads. Okay? So the probability of getting one head and one tail is 1/2, or 2 out of 4. Okay? Make sure you understand that how we got to that 1/2, or 2 out of 4. And then, of course, the probability of getting no heads is the same as the probability of getting all heads, 1/4, 1 out of 4 of these. Okay? So, and then we can express those as decimals as well. The next, when we come back, I'm almost out of time in this section, so when we come back, we're going to talk about graphing these and how we can move into more complicated population distributions, probability distributions.